Namaste, my friend, and welcome back to JEE Mathematics with Typical Monk. This is class 7, and today we meet an object you have probably already glimpsed but never truly used, the matrix. Here is something worth sitting with for a moment. Every linear system you will ever face, 2 equations or 20, quietly folds into one rectangular block of numbers. Hidden inside that block is a single number, the determinant, and that one number decides whether the system can be solved at all and how. When Lisa first saw matrix, she thought it was just a table dressed up in brackets. It is far more. It is a machine with its own arithmetic, its own rules, and its own inverse. Today, one idea at a time, we learn to operate that machine. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the types of matrices and the algebra of matrices, addition, scalar multiplication, and multiplication. Second, the transpose and the symmetric and skew-symmetric matrices built from it. Third, determinants, their properties, and the minors and cofactors that build them. Fourth, the adjoint and the inverse, singular matrices, and solving linear systems. And fifth, the JEE drills, a Cramer's rule word problem, a match, and a numerical quick check. So everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the raw object itself. A matrix is simply a rectangular array of numbers, arranged in rows and columns. An n by n matrix has m rows and n columns. The order tells you the shape at a glance. Every single number inside has an address. David calls the element sitting in row I and column J simply a sub ij. That address is how we point at any one entry without confusion. When the number of rows equals the number of columns, we call it a square matrix, and a square matrix carries something extra, a main diagonal, running from its top left corner to its bottom right corner. And 2 special square matrices deserve their names now. The identity matrix has one sitting on that diagonal and zeros everywhere else. The zero matrix is simply zeros throughout. Sit with these, every property we built today attaches itself to one of these shapes. Now, look at this figure, because it turns 2 matrix ideas into a picture you can actually see. First, the diagonal matrix. Only the entries sitting on the main diagonal are allowed to be non-zero. Every other cell in the grid stays empty. Second, the symmetric matrix. Here, the entry a sub ij always equals the entry a sub ji, so the grid is a perfect mirror image of itself across that same diagonal. Third, its close cousin, the skew-symmetric matrix. Now, a sub ij equals negative a sub ji, and that single rule forces every diagonal entry to be exactly 0, because a number can only equal its own negative if it is 0. And fourth, the operation underneath the whole picture, the transpose. Sayre's rule, flip every row into a column. So 3 by 2 matrix becomes a 2 by 3 matrix, and transposing twice always hands you back the original. Now we learn how matrices combine with one another. First, addition and subtraction. 2 matrices can only be added when they share the exact same order, row for row and column for column. You simply add the matching elements. Second, scalar multiplication. Take any single number k and multiply every element of the matrix by that same k, nothing more complicated than that. Third, matrix multiplication, the one that trips students up. A times b is only defined when the number of columns in a matches the number of rows in b, and each entry of the product comes from multiplying a row by a column and adding the results. And fourth, the warning John needed to hear early, multiplication is not commutative. A times b need not equal b times a, even on the rare occasion when both products happen to exist. Time to solve a full problem together, slowly, the monk's way. Solve the system 2x plus 3y equals 5 and x minus y equals 1 for x and y using determinants. Step 1. Write down what is given. 2 equations, 2 unknowns, and a coefficient matrix built from the numbers 2, 3, 1, and -1. Exactly the shape Cramer's rule wants. Step 2. Find the main determinant, called D. multiply along the main diagonal 2 times -1, then subtract the product of the other diagonal 3 times 1. D equals -2 minus 3, which is -5. Step 3. Find dx. Replace the first column, the column of x's coefficients, with the constants 5 and 1, and take that determinant. Dx equals 5 times -1 minus 3 times 1, which is -8. Step 4. Find dy. Replace the second column with the same constants instead. dy equals 2 times 1 minus 5 times 1, which is -3. Step 5. The answer. X equals dx over d, which is -8 over -5, 8 fifths. And y equals dy over d, which is -3 over -5, 3 fifths. Notice the path. Given main determinant, dx, di answer. The same 5 steps unlock every Kramer's rule question G can ask. Now the heart of the chapter, how a determinant is actually built and where it leads. Look at this grid and this flow together. First, the minor. Pick any element, delete its entire row and its entire column, and what remains is a smaller grid. Its determinant is the minor of that element. Second, the cofactor. Take that same minor and attach a sign, plus or minus, decided by whether the row number plus the column number is even or odd. Third, the determinant itself. Expand along any single row, multiply every element in that row by its own cofactor, and add all the products together. And fourth, the destination, the inverse. Collect every cofactor into a matrix, transpose it to get the adjoint, and divide that adjoint by the determinant. Lisa's warning: this division only makes sense when the determinant is not 0. Now sit up straight. These 5 lines are what G actually asks year after year. 1. The determinant of a product a B equals the determinant of a multiplied by the determinant of B, a clean, favorite one-line result. 2. The inverse of A equals the adjoint of A divided by the determinant of A, and it exists only when that determinant is not 0. 3. For system consistency, watch the main determinant D non-zero gives a unique solution. 0 can mean infinitely many solutions or none at all, depending on the other determinants. 4. 2 determinant properties worth memorizing cold. Swapping any 2 rows flips the sign of the determinant, and 2 identical rows collapse the determinant straight to 0. 5. The adjoint of an n by n matrix is always n by n as well. The order never changes, only the entries do. Let us drill the G way. I read a claim, you decide true or false, and if it is false, find exactly where the reasoning breaks. First claim, matrix multiplication, is commutative, so a B always equals BA. Let us check. Multiplication combines rows of the first matrix with columns of the second in a fixed order. Reverse that order, and you are combining entirely different rows with entirely different columns. So this is false. A B need not equal BA, even when both products happen to exist. Second claim, a matrix with determinant 0 still has an inverse, found from the adjoint. Think carefully. The inverse formula literally divides the adjoint by the determinant. So this is false. Dividing by 0 is undefined, and a matrix with determinant 0, called singular, simply has no inverse at all. Third claim, a system of equations has a unique solution exactly when the determinant of its coefficient matrix is not 0. Check the rule. That is the entire foundation of Kramer's rule. This one is true. A non-zero main determinant guarantees exactly one solution. A quick match now. Say each answer aloud before I reveal it. Symmetric matrix. This matches the transpose of A equals A. The grid mirrors itself perfectly across the diagonal. Skew-symmetric matrix. This matches every diagonal entry being 0. A number can only equal its own negative when that number is 0. Singular matrix. This matches determinant equal to 0 with no inverse. The adjoint formula simply breaks down. And diagonal matrix. This matches determinant equal to the product of the diagonal entries. Every off-diagonal term contributes nothing to the expansion. If all four came to you before the reveal, matrices are becoming yours. Here is a favorite G format. I read some statements. You silently count how many are correct. Statement 1. The determinant of the identity matrix is 1. Hold your verdict. Statement 2. A matrix and its transpose always have the same determinant. Think before you answer. Statement 3. Every square matrix has an inverse. So how many are correct? Two statements, the first and the second. The identity matrix truly has determinant 1, and a matrix and its transpose truly share the same determinant. But the third one falls. A square matrix has an inverse only when its determinant is not 0. Plenty of square matrices are singular. Two correct, statements 1 and 2. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. A B always equals B of 4 matrices. It feels natural. Ordinary numbers multiply in either order, so surely matrices do too. Sarah believed this for weeks. But here is the truth. Matrix multiplication is not commutative in general. Even on the rare occasion when both a B and BA exist, they can turn out to be completely different matrices. Myth 2. If the determinant is 0, you can still divide by it to find the inverse. Surely the formula still works if you just push through. The truth, division by 0 is undefined, full stop. A matrix whose determinant is 0 is called singular, and a singular matrix has no inverse whatsoever. There is nothing to push through. Time to test yourself, rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the ideas you built today. Question 1. What is the determinant of the matrix with rows 2, 3 and 1? 4. 2 times 4 minus 3 times 1, 5. Question 2. What is the order of the product of a 2 by 3 matrix and a 3 by 4 matrix? The outer numbers survive, 2 by 4. Question 3. What is the condition for a square matrix to be invertible? Its determinant must not be 0. Question 4. What does the transpose of a symmetric matrix equal? The matrix itself, unchanged. And question 5. If the determinant of a 3 by 3 matrix A is 5, what is the determinant of its adjoint? Determinant of a raised to the power n minus 1, so 5 squared, 25. If you caught all 5, you have truly understood today's class. Let us gather the whole class in one slow breath. A matrix is a rectangular array. Square matrices carry a diagonal, and symmetric and skew-symmetric matrices are defined by how a sub-ij relates to a sub-ji. Addition: a scalar multiplication act element by element. Multiplication needs the columns of A to match the rows of B, and it is not commutative. The determinant expands along a row using minors and cofactors, each one carrying its own sign. The inverse is the adjoint divided by the determinant. It exists only when that determinant is not 0. Cramer's rule solves a linear system with a ratio of determinants, and the determinant alone tells you unique, infinite, or no solution. At next class, we step into trigonometric ratios and identities, angle measure, the unit circle, and the compound angle formulas. Do not miss it. And so, my friend, we have learned to operate a genuinely new kind of object. It may have looked like just rows and columns of numbers, but understand this: the determinant you make today will return again and again in geometry, in vectors, in three-dimensional lines and planes, deciding whether things intersect, whether systems solve, whether transformations can be undone. Sarah, David, Lisa, and John all started exactly where you are right now with this one class. Be patient with yourself. Tonight, revise the difference between a singular matrix and an invertible one once, slowly. One idea at a time, you will crack JEE. Of this, I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you at the unit circle.